Hello students, welcome back. Finally, let's establish the grand conclusion here. We're going to prove this. Once we do that, then the second formula follows immediately because the Laplace transform is known to be one-to-one. So once you have this, then upon taking the inverse, we're going to get the second immediately. Now, how do we prove the first formula here? The inverse matrices are difficult to handle, so let me start from this. This times Laplace transform here. And we're going to work out, and then eventually we're going to prove it as I. That's basically what we want. If we have it, then flip it over to the other side. We're going to get desired results here. So that's what we are up to. But then again, it's not that simple, so we'll have to take one step at a time. And here's the first step. Let's distribute Si times this Laplace transform minus A times this Laplace transform. So for just a routine algebra, wait a minute, this is an identity matrix, so I don't really need to have it here. I can remove that. Fine. And no, never mind. Let's keep it here. Let's remove it in the next step. So S times Laplace transform and then e to the a t power. And then the Laplace transform is linear, so I can slip in this matrix multiplication here. Please recall the Laplace transform was defined in terms of integral. Do you recall that? Let's see, let's go back to, no, not here, over here, and the Laplace transform was defined in terms of integral. That's the Laplace transform, remember? Now, as for the integral, as we established here, I can always take this coefficient matrix out of the integral, or vice versa, into the integral. I can do it one way or the other freely because this coefficient matrix A is constant. For non-constant coefficient matrix A, we can't do this. If A is a constant coefficient matrix, we can do it, and in this case we are dealing with a constant n by n matrix, so yes, we can do this. So from here to there require the linearity of this Laplace transform, but actually it goes a bit deeper than that. The Laplace transform came from the integral, and then in the integral, constant coefficient matrix can go in or out. And this one's simpler, just removing this I, no problem there. Alright, now that we have A e to the AT here, or some students may wonder, why in the world did I slip this one inside? Okay, that's going to be answered right now. Please note that this is the derivative of this. Exponential always remains the same, and by chain rule, we have to multiply the derivative of the inside, and that's capital A, so we got that. So the derivative is actually A e to the AT. Or if you want to be a little bit more precise, we actually proved it in the previous subsection. Okay, alright, this is where we are so far. This one's all set, and here we can use the input derivative formula. What is the input derivative formula? Something is wrong. I am having a little bit difficulty with this mathematical notebook. Let me stop this playback. Okay, I got the control back. I don't know what happened. So here's the input derivative formula. Oh no. Oh, excuse me. Oh, this is not good. Hopefully it wouldn't crash on me right here. Does everybody recall this formula? Input derivative formula. And if you're unsure, you can always go back to page 123 and look up that Laplace table. There gotta be something like this there. And that's something we are gonna apply here because we have the derivative here. So if we do that, this whole thing here is gonna be S times the Laplace transform of the original minus y of 0, so I have to plug in t equals to 0. Does this make sense? I slid this one in, and that's because the Laplace transform is coming from the integral, and this is a constant coefficient. I can always bring it in, or you can call it the linearity, but that's a bit troublesome because the linearity property is used for scalars, and this is not a scalar, this is a matrix. So it's going to be better if you consider this as an integral, and then constant coefficient matrix can go inside or outside of the integral. Once you do that, this is the derivative. So we have the derivative. Now that we have the derivative, we can apply the input derivative formula. We can apply input derivative formula because this is basically the Laplace transform of each entry. You see, if you have 3 by 3 matrix, then we have 9 entries. And each entry we have the derivatives, and we have at each entry we have input derivative formula. So it's the same deal here. Let's simplify a little bit further here. Okay, if you plug in t equal to 0, then this entire thing is 0 matrix, isn't it? And then let's simplify. I can break up this parenthesis. And then this becomes now plus. Is my algebra correct? See? Input derivative formula, this whole thing became that. And then breaking up this parenthesis, minus and plus. And then plugging t equal to 0, we get 0 matrix. So e to the 0 power. We're almost there. We have s times this Laplace transform minus same thing, so these two will cancel each other out. And we have e to the 0 power. What is e to the 0 power? It's the identity matrix. So we got that. This matrix times that matrix is equal to identity matrix. That proves these matrices are invertible, and the inverse of this matrix is that, and vice versa. Inverse of this matrix is that, either way. Or I can simply say flip this one over to the other side. the Laplace transform of e to the at power is si minus a inverse, and that's the conclusion I wanted all along. If you look at it like this, it looks simple, but each step required something. So here, well, this was okay. The first step was just trivial. First step, no problem. Here, slipping a inside here, because Laplace transform is an integral. Basically, you're doing this. Constant matrix A can come out of the integral or vice versa, get in. And then we have the derivative. A e to the at power. That's the derivative. And now that we have the derivative here, we have the derivative of each term. So we can apply the input derivative formula for each term, and that's what this is all about. And then plugging in t equal to 0, we have a e to the 0 matrix, which is identity matrix. As for these two, they cancel each other out because I'm subtracting the same thing. So that's how we get this. I don't know whether this is going to be appropriate for exam level. Probably a little bit too hard, but at least it's still conceivable. Anyway, and the same thing, whole proof is it here. And once you have this, and then upon taking the inverse, you're going to get the second formula as well. So we got these. So what you're trying to do now is to do some computation of matrix exponential using the Laplace inversion. A little bit more comment here. Si minus a inverse is called a resolvent matrix, and in order for this matrix to be invertible, its determinant has to be non-zero. Yes. Okay. And then this determinant, Si minus a, is called a characteristic polynomial of the square matrix A. And we are using the same term, characteristic polynomial, for linear ODE. That's because they are closely related to each other. And it's a polynomial of degree n. And the zeros of this characteristic polynomials are called eigenvalues. And for the eigenvalues, the resolvent matrices do not exist, but otherwise resolvent matrices exist. So for eigenvalues, basically denominator is becoming 0, and let me see, the one-dimensional analogy was kind of like this. So the Laplace transform of e to the at, so this is the eigenvalue, and in that case I'm going to get s minus a is in denominator, so this whole thing is invalid. The only case that thing is invalid, that's the eigenvalue case. And this thing evolved into that expression for matrices, and that corresponds to eigenvalues. So theoretically they are related, and that's where I'm going to stop. I don't want to go too deeply into that. Instead, let's go to some application problems that we actually utilize this. I hope I have enough time for that. Okay, and how to calculate the resolvent matrix in general, but we are not going to consider a general case. It's just 2x2 case. So, alright, here we go. Find the resolvent matrix. How do we do that? Come on. Si minus A is that's it, isn't it? So this whole thing can be rewritten as S and therefore I'm gonna get S minus 3 here, and then this is gonna be 0 minus 4, and this is gonna be 0 minus of negative 2, and then this is S minus of negative 3. This is what we get. We want to find out the resolvent matrix. Okay, here we go. Si minus A inverse is 1 over, let's use the inverse matrix formula for 2 by 2. AD minus BC. So we need S minus 3, S plus 3, minus this one, minus minus plus, so I'm gonna get plus 8 here. And then I have to switch the principal diagonal and then take negative of the other diagonal, and there goes the inverse matrix. Okay, is it a good way to simplify this thing? Let's see, this whole thing is S squared minus 9, come on, squared minus 9 plus 8, so the whole thing is S squared minus 1. And therefore, this whole thing can be written as did I do this right? And then this can be split into each entry. I don't need this any longer. And then this too. And then this one too. And finally this one too. So that's the resolvent matrix. And then we have to take the Laplace transform of each. Looks like I'll have to take the decomposition by partial fraction of each. Ouch. So looks like I better just show you the solution, because the decomposition is gonna be really time consuming even if I use computer algebra system. By the way, here's the computation. The same deal. You see? S minus I and then inverse, so we use the inverse matrix formula. And here I didn't factor it yet. Here I factored. Either way, it's the same thing. Okay, I'll just keep it like this. And then, if you want to take the Laplace inversion, this thing, take the decomposition by partial fraction. Ouch. I just use, of course, computer algebra system. And thanks to these, I can take the Laplace inversion. And here's the solution. So that's how you can calculate the matrix exponential. Now that you have matrix exponential, calculate the solution. If you have appropriate initial condition, you can do it.